Okay, so now we're going to begin chapter 4, motion in 2 and 3 dimensions. In this chapter, you're going to learn, how do we define position and displacement in 2 and 3 dimensions, and also you're going to find how how to find the average velocity, instantaneous velocity, average acceleration, and instantaneous acceleration, and then we're going to move on to the study the motion of projectile and also circular motion, and we're going to briefly touch upon the relative motion in 1 dimension and 2 dimensions. Okay, so last time, so in chapter 2, you learned that when you have an object that's moving along the x-axis, in the y-axis, it's just in 1 dimension. So you can find out the displacement, and displacement is always the final position minus initial position. So now, if we expand what we have learned and then apply it to 2 or 3 dimensions, how do we express position vector and also the displacement vectors? So let's say we use a very generalized case when you have a 3 dimensions, then we use this R to indicate that's a position vector. And your R, of course, should have 3 components. You have the X, Y, Z component. So for the X component, let's just say it's X, okay? And then I hat, if we express the vector in unit vector notation, and then you have your Y, J hat, and you have your Z, K hat. So you can see that you have position vector that's expressed in unit vector notation, has X, Y, Z components. So that's an object initially at position R1, and then move into another position that's say R2 within the time delta t. So in that case, how would you find the average velocity then? So first of all, we need to express the object when it's at position R1, so you have that say x1 and then I hat and then plus y1 j hat and then plus z1 k hat. Okay, this is when the object initially is at, and then sometime later it moves to position R2, so it has a corresponding the S component, Y component, and then the Z component, okay? So in order to find the displacement is always the final positions minus the initial position. So you have the final position vector here, initial position vector here. So you can have just R2 minus R1. So in that case, you would just have your x2 minus x1. So you want to do it component by component. And then y2 minus y1. And then j hat, and then z2 minus z1, and then k hat. Okay, so you can see that it is exactly the same as what you had for the 1 dimensional, except that now you have this 2 additional terms here. One is in the y direction, one is in the z direction. So how do we find? So if we express this, your x2 minus x1, that'll just be delta x. So you have your delta x I hat, and then delta y j hat, and then delta z k hat. Okay, so you can see that your delta r, vector delta r, in unit vector notation, is just the displacement in the horizontal direction I hat, displacement in the vertical in the y direction, and displacement in the z direction. So how do we find average velocity? If you recall, the average velocity when you are dealing with the 1 dimensional is just let's say, if you remember, your AVG, if that's just 1 dimensional, that is delta x over delta t, right? So in this case, we're just going to extend this. So now instead of just doing 1 dimensional, now you're going to do it, in 3 dimensional case, you just have the delta r over delta t, and then so every term here is going to be divided by delta t. So what you have here is this. The average velocity vector is basically equal to delta r over delta t. And so you can have expand it, so you have the delta x over delta t, I hat, delta y over delta t, j hat, and then you have your delta z over delta t, k hat. Okay? So in that case, what you have here is that you can actually, say that this is your average velocity in the x direction, and then average velocity in the y direction, j hat, and then average velocity in the z direction, and then k hat. All right, so this is what we have here. So in shorthand, that would just be this. The average velocity is just basically equal to the displacement over the time interval. What about the instantaneous velocity then? To find the instantaneous velocity, remember, for all the instantaneous velocity, it would just be making the time so small, and then using this, you have your delta r over delta t. Okay, so what we have here is just that would just be your dr and then dt, and then r, of course, is this. You have your x, y, z components. Okay, so you're going to take the time derivative of each component. So that is that. Now, what about, so this is what we call the instantaneous velocity, and this is the average velocity. So what about acceleration? We're going to use exactly same thought that velocity is let's see. Before I do that, so let me just write it out here. So for you have your dr dx. So you have your d over dt, and your r is xi hat, yj hat, and then k and then zk hat. So what you're going to do is that you have your dx over dt, time derivative of the x component, I hat, and then dy dt j hat, and then you have your dz dt, and then k hat. Now, because they are all pointing in a direction that is perpendicular to each other, so you do not add them together. So you find your dx dt, and then have this is your the magnitude in the horizontal x direction, and this is the y component in the y direction, z component in the z direction. Okay, so realizing that this dx dt just instantaneous velocity along the horizontal direction, so we can use v and then sub x to indicate that's s component. Okay, we do the same thing for the y component, and we do the same thing for the z component. So in a three-dimensional case, you have the s, y, z component, and so this is exactly the same mathematical form like the position vector. Okay, so this is position vector, and this is your instantaneous velocity. So then the question is, these are expressed in unit vector notation. So how would you find the magnitude of the velocity v here, not the vx, vy, vz, the component, but the total velocity? In order to do that, those components are just the components along the x and y, z. So you're going to use the Pythagorean theorem in order to find out what the v is. So your v, the magnitude of v, would just be square root of vx squared plus vy squared, and then plus vz squared. Okay, and of course the angle would just be so you really have to draw the vectors in the x, y, z direction in order to determine what angle that is in reference to what axis. Okay, so that's that. And what about acceleration? For acceleration, now also, let me see, let me just draw here. The other thing is that, let's say on the xy, on the xy plane. Let me just erase this. So your x, the velocity is just basically dx dt. So if you plot it, let's say as a y and as x, so if you follow the trajectory of the object, let's say the object is moving like that, okay? So this is a trajectory of the object. And let's say at this instance, the object is right here. So you can see that what is the velocity then? The velocity is always tangent to the curve. So tangent to the curve, so this is the magnitude of v, and this is also the direction. Now at this point, it will be tangent to the curve, that will be here. At this point, that will be tangent to the curve, that will be here. So you can see that your velocity actually changes because the direction changes, and also the magnitude might change as well, okay? But suffice to say that, in order to find the direction of velocity, it is always tangent to the curve. All right. Now, what about acceleration? Acceleration is, so that's begin with the average acceleration. So the average acceleration is defined as, let's say in one-dimensional case, the average acceleration is defined as v2 minus v1 over t2 minus t1. This is when last, in chapter 2. So that's basically equal to delta v over delta t. So in a three-dimensional case, we have exactly the same thing, but now we have three components instead of just one. So you have the delta v. I'm going to use the sub x to indicate that's in the horizontal direction. And then you also have turn that in the y direction, and so forth in the z direction. Okay? So delta, not t. All right, so all these are delta, delta, delta. So you can see that they are exactly the same, except now I have to use a subscript to indicate that that's the velocity along the horizontal direction, along the y direction, and along the z direction. So in short, you can say that it is equal to delta v, okay, as a vector, and then over delta t. Because your delta v is equal to delta v xi hat, delta v j hat, and then delta z k hat. All right, so this is your average velocity, average acceleration. That is basically equal to the velocity difference over the time difference. So then how do we find the instantaneous acceleration? To find the instantaneous acceleration, which we drop the average, so that will be equal to, again, we're taking delta t to be approaching to 0. So we have your avg here. So you have delta v and then delta t. So in this case, your delta becomes differentiation sign again. So you have your dv and then dt. So again, you can see that we're using a vector form because we realize that they have three components. Each are independent from each other. So you have to have three components, x, y, z. There are situations that the acceleration may not exist in all three dimensions, and then you'll just have acceleration in one direction or two dimensions. Okay, so that's that. So in that case, what it means is that you will have the s component. So the s component will have the dvx over dt, right? This is dv dt. So dvx dt, and then your y component will have dvyx, dvy, and then dt, and your z component is this. So your acceleration can be expressed as the s component I hat, the y component j hat, and then the z component k hat. Okay? So once you know the components in each direction, then of course you figure out what is the total acceleration. Because these are in unit vector notation, they does not represent. Neither one of them represents the total acceleration. So what is the magnitude of the acceleration? The magnitude of the acceleration, of course, again, you're going to use Pythagorean theorem. So your A here would just be the square root of the s component square, the y component square, and the z component square. You add them together and take the square root of the sum, and that gives you the magnitude of the acceleration. Okay. Now, what about the direction? For directions, again, you will have to plot it on the x, y, z axis in order to see which direction the vector is pointing, and then find out use the diagram in order to figure out how to find the theta. Okay, and that might be, you know, instead of just one angle, you might have like 3 angles, each with respect to the x, y, z, you know, direction. Okay, all right. So I will stop here.